Welcome to Module 1 and our first lecture on systems thinking. In this lecture, you will be introduced to the concept of systems thinking, some of the terminology that we use in applying systems thinking, and you'll also have an opportunity to apply systems thinking to a real-life problem. Why do we need to hone our skills in and our ability to think in systems? The world we are operating in, both as business owners or organizational leaders, is very rapidly changing. Product life cycles are decreasing at a very fast pace. Organizations face hyper competition, pressures to become more sustainable, and businesses themselves are becoming very complex social systems which are highly interconnected at a global level. In trying to solve complex organizational problems, systems thinking can become a very useful tool. Typically, when we are faced with an organizational problem, we tend to approach it in a reductionist perspective. The reductionist views see system as function of their parts. Every system is a function of its individual parts. And so in order to better understand a system, we break it down into its individual parts. This analytical thinking helps us understand what each part does and how it works. What this approach overlooks is the interconnectedness between the elements of a system. A system is a set of interconnected elements organized in a way that fulfills a function or meets a purpose. The systems view also considers how the system's parts are interconnected. This type of synthetic thinking explains or helps us explain why the parts do what they do, not just what each part does and how it works. Let's look at an example. If I were to ask you, what is the relationship between wolves and rabbits? You might think, well, this is fairly simple. Wolves eat rabbits. It's a linear relationship. Rabbits are the prey and wolves are the predators. This is a reductionist view, a form of linear thinking. It does not consider the interrelation between the wolves and the rabbits. If we try to think in a more systems perspective, a cyclical relationship rather than a linear one, we might recognize that in fact, the relationship between the wolves and the rabbits is interconnected. The predator-prey relationship is going to influence both the rabbit and the wolf population because the two are interdependent. How does that work? If the rabbit population grows very rapidly one year, the wolves are going to be very healthy, there's going to be ample food, and they're going to be able to have more births the following year, growing the wolf population. As the wolf population grows, this might lead to a decline in the rabbit population, more predators. As the predator population declines, so will the wolf population, because there will be less food and so fewer births in the wolf population for the subsequent year. So you can see that the relationship between predator and prey is actually quite cyclical and not linear. Of course, this system, this simple system that we're looking at right here, doesn't consider certain things that fall beyond the boundaries of this particular system. Very often in systems thinking, we try to simplify in order to identify relationships between elements in a system. And so, of course, here we're not considering things outside the boundaries of our system, for example, variables that might influence the growth of the rabbit population or other predators beyond wolves. As mentioned earlier, a system is a set of interconnected elements organized in a way that fulfills a function or meets a purpose. Can you think of any systems that fit this definition? You might want to pause the video and jot down a few examples. For example, a football team. Is that a system? How do we know if what we're looking at is a system or just a random collection of things? We can use this tool to help us determine whether what we're looking at is in fact a system. So let's apply this to our example of a football team and counter it with a very simple example of a pile of laundry. Are there parts? There are certainly many parts to the pile of laundry, and there are also parts to the football team. Players, coaches, rules of the game, referees. Do the parts affect each other? In the laundry pile, not so much. What about the football team? Absolutely. The morale of one player might positively rub off on another player and motivate him, or a certain pass by one player might enable another player to score a point. Does it matter how the parts are arranged? If I pour out all the laundry from the laundry basket onto the floor, it's still the same pile of laundry. It doesn't really matter how the parts are arranged. What about the football team? Yes, each player has his role. The rules of the game apply to all of the players. And so how the parts are arranged does matter. Does the behavior of the system change if a key part is taken away? If we remove one item of laundry from our pile, we're still looking at a pile of laundry, maybe slightly smaller, but still a pile of laundry. If we remove a player from a football team, or if we remove a referee, or if we change the rules, we're no longer looking at the same game. And so the behavior of the system is going to change if a key part is taken away. A very good example for that is the human body, another system. If we take out a particular organ, in most cases, the human body will no longer be able to function if we lose a specific organ. And so the system, the behavior of the system is going to change if a particular part is taken away. Does the interaction of the parts produce an effect that is different from that of any of the parts on its own? And again, the answer here is yes for our football team. The game depends on each element, each player, the rules of the game, the referees doing their part. So we've determined that a football team is indeed a system. So is a city, a system of interconnected transportation, infrastructure, residential areas, commercial areas, organized in a way that fulfills a specific purpose, and the elements are all interconnected. A factory is also a system, as is the human body, a tree, an animal, and even a forest. A forest is actually a larger system that within which are embedded other smaller systems. So a forest is a large system. A tree and an animal are smaller systems embedded in the larger system of the forest. It's important to understand that we can change certain elements of the system, and system elements can change, but it will not change the actual system if the purpose and interconnections remain unchanged. For example, we can replace a particular player on a football team, but if the interconnections and the purpose remain the same, we're still looking at a football team. We can replace a particular employee in our factory, but if the interconnections among employees and the purpose of the factory remain the same, we're still looking at the same system. If you were to conduct an internet search for a definition of systems thinking, you might find lots of different definitions. Systems thinking is defined as a conceptual framework that helps us identify patterns to help us see how to change patterns effectively. Another definition identifies a system as a set of interconnected elements operating together to achieve a certain function or purpose, where the collection together produces its own pattern of behavior over time. It might be challenging for us to identify the purpose or the function of a system, and we have to be careful not to assume that the stated purposes of a system are indeed the purposes of the system. For example, a government might state that environmental protection is its purpose, but if the behavior on the system does not work towards this goal, for example, if no resources are dedicated towards this goal, is this really the purpose of the system? So the purpose of the system is not always going to be clearly identifiable to us, and we have to be cautious when we seek to identify the purpose of a particular system. Systems thinking is going to give us a different perspective from traditional analytical models that seeks to separate parts for individual study, the linear thinking that we looked at in the beginning. Systems thinking also develops our understanding of the interdependency among the different variables of the system. And we look at different behaviors and potential feedbacks within the system that produce its results. Let's look at some basic terminology in systems thinking. In systems thinking, we will very often use stock and flow diagrams or stock and flow models, as well as behavior over time graphs, to help us make systems more visible, to understand systems better. Of course, we've discussed earlier system boundaries. If the objective of using stock and flow diagrams is to simplify in order to facilitate understanding, we will not always be able to include everything beyond the boundaries of a system. This is what these little gray clouds represent, things that happen beyond the boundaries of the systems. One key term in systems thinking is stock. Stock are the elements of the system that we can see or count or measure in any given moment of time. These can be physical objects, but don't have to be. For example, the number of employees in our factory, that's our stock. But the stock of knowledge of our employees in our factory is also a stock, even if it's not a tangible stock that we can easily count. The flow includes both inflow and outflow, are the changes in stock over time. Systems operate in a dynamic equilibrium, seeking to sustain the system itself through inflows and outflows. Stock and flow diagrams help us visualize or quantify the interconnected accumulations, the stocks, and the input and outputs, the inflows and the outflows. For example, population size can be a stock. The inflows are the births in a given year or a given period of time, and the outflows are the death or the number of deaths in that same period of time. By looking at stocks and flows, we are better able to identify how one variable influences another variable to determine what behavior this might result in. Think at our wolf and rabbit example. Inflows and outflows, right? So if we think about the stock of the population of wolves or the population of rabbits, what influences the growth of that population, what influences the decline of that population. It's important to note that stock can take time to change because inflows and outflows are not instantaneous. For example, if my stock is literally my stock of inventory in my store, in my retail operation, and the outflow are all the sales, the inflow is going to be the new inventory that I order. But once I place my order, it might take time for the inventory to reach me. We've all experienced that during the supply chain crisis as a result of the COVID-19 pandemic, which can result in fluctuations in the stock I have on hand. Another tool that we use in systems thinking are behavior over time graphs. Because the relationship or the interconnections between systems variables manifest themselves over time, it might make it difficult for us to make decisions. If we are able to graph the behavior of variables over time, it can help us identify what relationships are driving the behavior in the graph. Again, think about the wolf and rabbit population. We need to look at least a couple of seasons to see how the fluctuations in the size of the wolf and rabbit population are influencing each other. And so in this case, the x-axis, the horizontal axis, is going to be time. And this can be hours, days, months, seasons, or years. Whereas the y-axis, the vertical axis, is the behavior that we're looking at. By graphing behavior over time, we can see gradual increase, gradual decline, or fluctuations. For example, in the example of the population size, if births are larger, or the number of births in a given time are more numerous than the number of deaths, we're going to see growth. If the opposite situation happens, if the number of deaths are larger than the number of births, we might see a decline. Oscillations in behavior over time are due to a delay in feedback. For example, if we're ordering inventory for our store, it takes some time when we have inventory and we're selling, it takes some time before we receive our new order to reach again the desired level of inventory on hand. Systems seek to maintain what we call dynamic equilibrium. Systems run themselves through feedback loops to try to maintain dynamic equilibrium. If we want to change a system, we have to identify the feedback loops within the system. Feedback loops are what operates within a system to generate more inflow or less outflow. Let's look at some examples. A balancing feedback loop is a situation in which the feedback within the system brings the system close to equilibrium over time. For example, if I'm seeking to heat a room to 70 degrees, every time the temperature drops below 70 degrees, the furnace will kick in, seeking to reach this dynamic equilibrium of 70 degrees inside, a balancing feedback loop. A reinforcing feedback loop is based on the idea of exponential growth, whereas the feedback loop reinforces continuously. Let me give you two examples. One reinforcing feedback loop can be negative. For example, if we use the example of soil erosion, the more soil that is eroded, the fewer plants are able to grow. The fewer roots we have in the ground to hold the soil in place, the more soil erodes, and so on and so forth in a vicious cycle. Reinforcing feedback loop. Of course, we can also have a positive situation, one that we would all like to see in our bank accounts, right? The more money we have in our bank account, the more interest we will earn, which will result in more money in our bank account, which will result in more interest, and so on and so forth, in a virtuous cycle. This idea of exponential growth. Of course, we can have more than one feedback loop operating at the same time, which means we are facing a situation of competing feedback loops. Let's look at some examples. Let's look at two examples of competing feedback loops. The first one consists of two competing balancing loops. If you think back at the example of the furnace, the balancing loop inside the room is one that causes the furnace to kick in every time the temperature drops below 70. Let's say that's your desired temperature. That's a balancing feedback loop. This feedback loop might be competing with a different feedback loop that we're very familiar with in Boone Winters. When the temperature outside drops, the balancing feedback loop that's competing with our furnace is when the outside temperature drops, the balancing feedback seeks to balance the temperature in the room with the temperature outside, causing heat to leak to the outside, which makes our furnace work harder. This is a situation of two competing balancing loops, one seeking to balance the temperature in the room and the other seeking to balance the temperature inside and outside. Another example is inventory management. Our stock of inventory keeps changing while we're trying to control it, right? Every time we sell an item, we ideally would be able to replace it with new stock so as to keep the stock at a certain level. Of course, as we mentioned earlier, there might be some delays in the system. The time it takes for us to receive new inventory, and so we might see oscillations in our desired stock over time, right? If we graph this over time on the x-axis, y-axis is the inventory we have on hand. A different situation might be one in which the competing feedback loops consist of one balancing loop and one reinforcing loop. If we think about the population example, the reinforcing loop is the birth rate, and the balancing loop is the rate of mortality. It depends on which feedback loop dominates the system. If the dominating feedback loop is the reinforcing loop, the reinforcing loop, the birth rate, we might see an increase in the population size because the dominance is on the side of the reinforcing loop. If, however, the situation is different and the dominating feedback loop is the balancing loop, the mortality, meaning that mortality exceeds birth rate, we might see a decline in population size over time. And so it will depend which one of the two feedback loops dominates the system. And that will have an impact on, in our example, the population size over time. Another example is investment and depreciation. The reinforcing loop is investment. We might invest in our factories or our organizations by buying more physical capital like machines or more factories, and investing in our human capital, training our employees to boost efficiency. And this will drive our output, the stock of goods and services. So here we might look at behavior over time, and the stock that we're looking at are the goods and services that we are able to produce. At the same time of the reinforcing loop, the investment feedback loop, we also have a balancing feedback loop, which is depreciation, right? The physical obsolescence of our machinery or a factory, or even the skill set of our employees, which needs to be updated periodically to keep up with changing technologies, for example. This is the balancing loop. And so again, if we're thinking about which loop dominates, if the investment, the reinforcing loop, is one that dominates, continues to be greater than depreciation, which is the balancing loop, we might see a growth in our output, in our goods and services. If, however, it's the balancing loop that dominates the system and the rate of depreciation exceeds the rate of investment in both physical and human capital, we might see a decline in our output of goods and services or stock. And this is a great example for recognizing that our stock can be influenced not just by the balancing loop, but also, or by increasing the balancing loop, but also by decreasing the reinforcing loop. We can improve or increase our output by increasing investment, right? Investing more in newer machinery or more skilled employees or training our employees. But we can also slow down the balancing loop by slowing down depreciation, for example, by buying better machinery or extending the life of our machines and in our factories to slow down depreciation. So this is a great example to see how we can take different approaches in how we manage feedback loops, both balancing loops and reinforcing loops. And so it's not just that we can grow our stock here, our output, our goods and services that we produce by increasing investment, the reinforcing loop. We can also increase our output by slowing down the balancing loop, the rate of depreciation. A few more points before we get to actually practice using systems thinking in a real life situation. What is system analysis? System analysis seeks to identify the driving forces and how the system reacts to those forces. This helps us predict what would happen if certain driving forces unfold. For example, if we think about population size, some governments in past decades have tried to control population growth by penalizing families for having more than one child. This is an effort to reduce the inflow, the birth rate. Other governments who sought to grow their populations did the opposite and incentivized people to have more children by trying to increase the inflow. So a systems analysis is a process that we use to try to identify driving forces and how the system might react to those forces. And this might help us be able to influence the system. We discussed shifting dominance in the previous slide when we have two feedback loops that operate simultaneously, two balancing loops, or a balancing loop and a reinforcing loop. It depends which feedback loop dominates the system in order to identify future outcomes. Another important aspect that we need to consider are system boundaries, those things that happen in the gray clouds, right, outside what we represent in our system. These variables or forces that operate outside what we look at in the particular system might be also important in considering or influencing our inflows and our outflows, our flows and our stocks. For example, social trends regarding social norms regarding family size and gender roles within the family might influence the birth rate. In most developed nations, dual career households are becoming the norm, which is influencing the birth rate, and that families are becoming smaller and people are having fewer children. So this is happening outside of our depiction of the population size system, but we can't ignore those factors that happen outside the system and might influence how the feedback loops in our system operate. Every system will extend beyond what we can show in the model. The model is used to simplify, to help us understand the system, but we can't ignore those limitations or those factors outside the boundaries of what we can depict in our model. We also have to identify system delays. For example, if our stock is the stock of fish in a particular lake or in a part of an ocean, the inflow is the growth of the fish population through new birth of fish, and the outflow is what predators eat or what humans fish. And this is why systems thinking is so often used in the study of sustainability, because it helps us understand system delays. What is the system delay in the fishing example? The stock is the amount of fish in the ocean. If we allow overfishing, that would increase the outflow, and it might take the system much longer to replenish the stock of fish. That's a system delay. The more the fish population is depleted, the longer it's going to take for the fish to recover to previous levels. This is why in many parts of the world, governments or local authorities are limiting the amount of fish that can be harvested by commercial fishing every year to make sure that we don't allow the system to fall to a level of stock that is so low that's going to create some significant systems delays in replenishing the system. Other constraints that we have to consider that happen outside the boundaries of the graphic depiction of our systems models are the environmental constraints, right? For example, in population growth, the number of births every year is going to also be determined by some environmental constraints, right? Population or people need food, healthcare, education, and so the amount of inflow will be constrained by those environmental variables. If you want to think about a business example, a new product can grow significantly. Here the stock would be market share, for example, but this will at some point also reach market saturation. Most systems cannot grow indefinitely. Most systems will be constrained by their physical environment. And those physical constraints can also shift dominance from the reinforcing loops to the balancing loops. If we allow for overfishing, then the dominating loop will be the balancing loop, not the reinforcing loop. In this final part, we're going to look at a real-life example and apply systems thinking to a particular organizational problem. In order to do this, you're going to need to stop the video and pop over to your As You Learn page. In the first module, look for the article titled "Soda Companies Are Becoming Possessive of Their Trash." You need to read this very short article and then come back to this video. So if you've read the article, you understand that companies manufacturing beverages, let's focus on soda brands to simplify, although every beverage manufacturer is probably faced with a similar problem. Soda brands need plastic bottles to bottle their drinks. Our stock in this example would be, right, plastic bottles. What's the inflow? What's the outflow? The inflow consists of all of the plastic we can purchase to produce plastic bottles. the inflow can consist of either new plastic or recycled plastic. The stock is the number of bottles or the amount of plastic that we have on hand, and the outflow is the plastic bottles that we use to bottle our beverages and sell them. If we try to think at the feedback loops of the feedback loops in this system, what influences the inflow? What influences outflow? What can we do to shape inflow and outflow? And so first we have to think about the feedback loops at play that shape the inflow to this organization. What happens in this gray cloud? If you've read the article, you understand that the price of recycled plastics is rising globally. The price of oil, which is the raw material used to make new plastic, is also rising globally. At the same time, many companies like Coca-Cola and Nestle have made green packaging commitments to reach a certain threshold by a certain period of time and use more recycled plastic in their products. It's not just organizational commitments, but also government policies and new legislation that set a minimum of recycled content levels for plastic packaging. For example, in California, companies will need to use 50% recycled material in bottles by 2030. Similar legislation is happening in Europe and other countries. And so the pressure, the feedback loops that influence the inflow are happening at the global level, not just a domestic level. Another challenge that influences our system here is that the beverage companies are not the only ones using recycled plastic. In fact, they only use about 30% of the recycled plastic available, and they're competing with other industries in clothing, carpets, cosmetics packaging, and auto components, which all use recycled plastic. 70% of the recycled plastic goes to those industries. And so we understand some of the complex global forces at play that influence our inflows. So what can we do? What solutions can we identify if we're a soda brand in need of more plastic bottles and in need of more recycled plastic bottles to reach our own commitment or governmental regulations as to the percentage of recycled plastic that needs to be in the bottles that we sell? And this is where feedback loops and understanding of inflows and outflows can help us. What are some of the ways in which companies can increase inflow, or some of the ways in which companies can increase outflow, decrease outflow? What reinforcing loops are at play, what reinforcing feedback loops are at play that can help us shape inflow, and what balancing feedback loops are at play that can help us shape outflow? And so again, you might want to pause the video and jot down some ideas and think about ways to address this complex problem faced by soda brands. So one feedback loop that organizations can use to increase the inflow is to invest in recycling programs, both establish more plants for recycling plastic and invest in collection of used plastic to feed into those plants that produce recycled plastic usable for the plastic bottles. That's one feedback loop that we can focus on to increase inflow. Of course, another way to try to increase inflow is reduce competition for recycled plastic. As of yet, legislation is mostly focused on the beverage industry and the plastic bottles. These companies in the beverage industry could lobby for government regulations to put similar restrictions on other industries using recycled plastics. If you've been following the news, the EU is putting in place some significant restrictions on fast fashion manufacturers, for example, to make their clothing more sustainable and recycle more of the discarded clothing. And so by lobbying to put similar restrictions on other industries competing for the same raw material, plastic bottles or recycled plastic, we can influence the inflow. As we saw earlier, we can also increase our stock by reducing outflow. And you might think about creative things that soda companies are doing to reduce the outflow, to reduce the amount of plastic that they use. More companies are using aluminum bottles. Some companies are coming up with creative solutions to sell their beverages in powder format or tablet format that consumers can then mix with water at home and reduce the amount of plastic that is used. So hopefully this example has helped you see how systems thinking can be used to address complex problems in organizations. And you'll get to do that in your first assignment as well.